So we've talked about periodic motion and oscillations in Chapter 14, and now we're going to be talking about how that relates to wave motion. So we have to know what we mean by a wave. What a wave does, and there's different types of waves: earthquake waves, sound waves, waves on strings, water waves. Those are all mechanical waves. Then you have electromagnetic waves, which is light and radiation. All waves have the property that what they do is that they transmit energy, not matter. So waves transmit energy from some initial disturbance or oscillation. They don't transmit the actual matter. The actual atoms don't get transmitted with the wave. So a water wave or a wave on a string, it's not a particle in the string that's physically moving. Instead, it's the energy from some initial oscillation that then gets carried away by the wave. So the wave carries that energy away from the initial source of oscillation. So there's going to be two main categories, and these are divided into mechanical waves and electromagnetic waves. So mechanical waves and electromagnetic waves. In this semester on mechanics, we're focusing on mechanical waves. In the next semester, when you talk about light and optics, you'll come back to the idea of electromagnetic radiation. Now, a big difference between these is that mechanical waves do require you to have some medium, some matter, some atoms, in order to propagate the wave through. So these mechanical waves require what we call as a medium to propagate through. So sound waves, for example, or mechanical waves, could not propagate through the vacuum of outer space. So there's no atoms there to carry that energy away from the initial source of the oscillation. So common examples of mechanical waves are sound waves, earthquake waves. There the medium is the actual earth itself. Water waves, medium is the water. Waves on a string, etc. Now, electromagnetic waves, to contrast, they do not need a medium to propagate through. So a laser pointer can be shown through a vacuum jar and it's undisturbed, and similarly we can send radio waves in through outer space. They're a type of electromagnetic waves. Now, this, instead of actually having physical atoms that are oscillating as that energy is carried away, an electromagnetic wave is an electric and a magnetic field that are oscillating. And next semester you'll see how an oscillating electric field creates an oscillating magnetic field, which creates an oscillating electric field, which creates an oscillating electric field, and then that gets propagated and carried away from the original source without needing the interaction of atoms to carry that energy away. So the waves that we are focusing on, like I said, are going to be the mechanical waves, where you do actually rely on the interaction between atoms in a medium in order to have that energy be transmitted from one place to another. So within mechanical waves, there's going to be two subtypes of mechanical waves. The first is going to be called transverse, and the second is going to be called longitudinal. And I drew these side by side to contrast what they are. So if you have your direction of the wave travel, say this is your velocity of the wave, so that's the direction that the energy is going to be transferred in that direction. Then a transverse wave is when you talk about the individual atoms and particles in a wave, that they're going to oscillate up and down perpendicular to the direction of the wave motion. So here, this would be the particle oscillation, and that's again going to be perpendicular to the direction of the wave motion, so the direction of the wave velocity. So an example of this would be, say you shake a string up and then down, and then that causes a particle on the string to go up and then down. And then as the disturbance propagates down the string, then every particle then moves up and down as that wave passes through. And so the individual oscillations of the particles move perpendicular to the velocity of the wave. A longitudinal wave, on the other hand, you might guess, is that if your wave direction is again towards the right, now as the wave passes through, individual particles will oscillate parallel to the direction of the wave motion. So in this case, the particle oscillation is parallel, so it's along the direction of the wave velocity. And the most important longitudinal mechanical wave is going to be sound waves when we get to that specific section. So specifically, say, as I speak in class and the sound wave comes from my mouth to your ear, the air molecules in the air are actually then oscillating as that sound wave passes through them parallel to the direction of the wave velocity. And so they then oscillate. The wave, say, travels this way. They oscillate back and forth as that wave propagates through. So let's go ahead and begin and try to come up with a mathematical representation for the waves. So let's come up with a mathematical representation for wave motion. And to understand this, let's take a simple snapshot of a wave, which when I call a snapshot, it's imagine just at one moment in time taking a picture of some sort of disturbance. And for now we won't make it sinusoidal, we'll just have, imagine you shake a string up and down, and then that initial disturbance that you have. So let's say that it might look something like this. If here's my string, and I shook it up and down one time, and then I created this pulse on the string. So if this, then I take a picture of what it looks like at t equals 0, then I can take this snapshot, which is also called a waveform, which is equal to, again, the idea of just taking a picture of the wave at some fixed time. And that's what we call the waveform, because it's the form of the wave. It's the shape that the wave takes on. Now, if that's at t equals 0, then that's going to be y as a function of x. Again, that's the waveform. And then in order to describe the wave fully, we need to know what it's doing at all times. So what we need then is some expression for y as a function of x and t, right? So the waveform essentially as a function of time. Now here's where you have to keep your variables straight, right? X is the direction of the wave motion. This is an example of a transverse wave because the individual particle oscillation, say a particle on the string, is perpendicular to the direction of the wave travel. So the transverse motion here in y is now telling you the individual particle's motion in a transverse direction perpendicular to the wave direction of motion, which is x. So x is the direction of motion of the wave, y is what an individual particle is doing, and then time is obviously what would happen as a function of time. So at some fixed time, you just take a picture and you end up with what you have here. But if we want y as a function of x and t, then let's just say that y is a function of x at t equals 0, so y, x, 0, that we're going to just say it has some shape, f sub x. So we'll come up with some arbitrary way to describe it at a later time t. So let's say here this has some f sub x is the shape of it. Now, at some later time t, we want to know where it is and what it's doing. And so if you imagine, let's say this one is traveling to the right, you pluck it and then this wave travels to the right, what you imagine is that you would have this same shape, but then at some point it would have moved over by some distance. And this distance that it's moved over is actually equal to the speed of the wave times the time, right? X is equal to the velocity times the time. So this would be equal to the velocity of the wave times the time. So at some later time t, we can say y as a function of x of t is actually going to be equal to y as a function of x minus vt, whatever this f of x is, at 0, at t equals 0. So it's going to have the same shape. So this step probably was a little confusing for those that haven't done this recently in your math courses. But imagine, say, shifting a parabola over, right? That's a common example that's often used. Is you have the equation for a parabola, and then you want to shift it to the right, or you want to shift it up by 2, right? Then what you end up doing is, if you want to shift it to the right, you then take x minus however much you want to shift it to the right. So it's going to be the same shape here, which is why I still said it's going to have that same behavior at t equals 0, but now it's just going to be shifted to the right by vt. So what that lets us conclude then is that y as a function of x and t is going to be equal to f sub x, the same exact function, except for x minus vt. So it'll be shifted to the right. And this is, again, if it goes to the right in positive x. So we can take any function of our initial wave form, and then we can see what it is as a function of time if we know the wave speed. Now, as you might guess, if the wave goes to the left, then you would then have y as a function of x and t is equal to f and x plus vt. So whether or not this is a minus or a plus, when you start seeing these equations and we become more comfortable with them, will tell you whether or not it moves to the right or to the left. Now, commonly we'll be talking about wave motion that's not just a single pulse, but say has some periodic motion to it. And the easiest case of periodic motion, as we have seen, is simple harmonic motion. So let's look at the case of a sinusoidal disturbance. So that you shake the string up and down, up and down. And again, this would be our simple harmonic motion from, say, chapter 14 that we've discussed previously. So f as a function of x at t equals 0, right, is going to be our f of x comma 0. And that's going to be equal to some amplitude, a. And now I'll choose, because I chose a sinusoidal disturbance, so I'll just put it in as sine. And then here, I'm going to put in 2 pi over lambda, and I'll define lambda in a second, times x, plus phi. And then this would be equal to the position of a given particle as a function of its position at t equals 0. So now, note that this is different than what we did in chapter 14, where we were then looking at a single particle that was oscillating up and down, and that we then talked about that oscillation as a function of time. This is now coming up with the waveform of this graph. So again, this is going to be a plot of y as a function of x. So this is the waveform. And that's then what we're going to use in order to come up with the actual equation for the wave at all times. So we have some initial sinusoidal disturbance, and this is y as a function of x. And all this is the equation for this wave. In this particular case, I put in a phase constant phi, but we can see I've drawn a standard sine wave, so that phi would be 0. So if we're going to write out this equation, then we want to know basically what the cycle of the wave is. Now, it's not y as a function of time, it's y as a function of x. So we no longer are talking about this being the period. We can't get the period from this information alone because this is now taking one time and just taking a picture of the wave. The graph looks the same, but you got to read the axes in order to know what you're looking at. So this here is actually what we call the length of one wave cycle, and that's what we call the wavelength. And that's what lambda is. So that's the length of one wave cycle, which is defined to be the wavelength, and that again is lambda. Now, if we then go ahead and look at this expression here, we can see that then 2 pi over lambda makes sense for how you would then write this expression, because when lambda equals, when x equals lambda, then you would have this equaling 2 pi, and you've completed one cycle. Okay, so that's what lambda is, and then phi is again our phase constant, and that depends on where t equals 0 again. In this case here, phi is equal to 0 for this diagram. Okay, and then one last definition that I'll put down related to the wavelength is that we have k, which we'll use. This is different than the spring constant k. This is a new k, so be careful with your equation g, which is equal to 2 pi divided by lambda. And that's sometimes used instead of the wavelength. So this is considered the wave number, this is considered the wavelength, and you can see that reason that we would have that because now we can say that y is a function of x and 0 is equal to a times the sine of kx plus phi. So it's just a little bit easier than writing 2 pi over lambda out all the time. Okay, so if this is our now y as a function of x and 0, if we recall that then that would be our function f of x, then to write the expression y as a function of x and t at all times, we simply need to subtract minus vt from this in order to write our full equation. So what we can do then is say that y as a function of x and t is equal to, again, our function of x minus vt, which then is going to be equal to a times the sine of, and now in this case, I'll leave it in terms of my 2 pi for now, for clarity, 2 pi over lambda, and then here x turns into x minus vt, and then plus phi. So this is now the expression, so the general expression for a sinusoidal wave traveling to the right. It'd be a transverse sinusoidal wave because we're now talking about the vertical transverse position as a function of x. Okay, so I've rewritten this expression here just so we have it for this new sheet. And again, this is for a traveling wave in the plus x direction. And if we go ahead and we look at this, then what we can talk about is the wave form, right? Y versus x would give us the waveform. And then we can also plot y as a function of t for this. And y as a function of t then would be at a fixed location x. And so it might also have this same shape, right? So this is now going to be for a fixed x. This waveform is for a fixed time. This one is the one where we could get wavelength. This one is the one where we got the period of the oscillation. And this would be for a fixed position, what is one particle doing? So this is showing the particle's oscillation, one particle as a function of time at some location x. This is showing the picture of the whole wave, y as a function of x at some fixed time. And so you have to be, again, very careful of reading your axes in order to determine this. But if we imagine then a single particle, right, a single particle oscillation follows simple harmonic motion. And that's from chapter 14. And so we know, just like we did then, that the max transverse speed of a particle in the wave is going to be equal to what we'll call now Vy max, so the maximum speed that something oscillates with. And we saw before that that was equal to omega times A, where A is the amplitude of this oscillation. And the maximum acceleration is still going to be equal to omega squared A. And again, that comes from our previous chapter and understanding simple harmonic motion. Note, though, that this is not wave speed. That's the individual particle's maximum speed, which is different than the speed at which the energy is being transmitted, and that is the wave speed. And then here is possibly the most important equation for wave motion, which is that the wave speed, which again is the speed of energy transmission, is equal to what we call V, and that's equal to the wavelength multiplied by the frequency. And this is true for all waves, even electromagnetic waves. So now we can write down a large number of relationships. We already had a bunch of expressions in terms of omega, in terms of F, in terms of T, and lambda in terms of K. So again, refer to the equation sheet which is posted online to see which ones you're provided with and use that when problem solving. You have that the wavelength, as we've said, is equal to 2 pi over K. We recall that the frequency is equal to the angular frequency divided by 2 pi. So we can see now that if we plug in these values here, that the speed, which is equal to lambda f, is going to be equal to omega over K. So that's another way to write this expression. So if we do that, and we go back to this first form here, we can see that we have 2 pi over lambda, and then times x, and 2 pi over lambda times v. So I'll rewrite it again real quick. Y as a function of x and t is equal to a times the sine of 2 pi over lambda x minus vt plus phi. And so then that's going to be equal to a times the sine, and this is just k, so kx, and then minus 2 pi times v divided by lambda. V is lambda f, so this becomes 2 pi f, and 2 pi f is simply omega, so that's minus omega t, and then plus phi. So a slightly simpler way of writing the general form for this traveling wave to the right in terms of the wave number and the angular frequency. All right, so let's do one example related to understanding this mathematical representation of a transverse mechanical wave. So let's say that you have a transverse wave that moves along a string. That implies then it's a mechanical wave. And it's moving to the left now, not to the right, along the x-axis. And you're given the amplitude 0.1 meters, frequency of 10 hertz, and the speed of 100 meters per second. The question then is, what is the equation for the wave, and what is the max transverse speed of a given particle on the string? So for part A, we want to have y as a function of x and t, and then we're just going to write down equals a times the sine of kx, and now I want to write plus omega t plus phi. So remember that the plus means that it's traveling to the left in the negative x direction. So I have to have that plus sign there and I have to know to add it because I was told in the problem that it was moving to the left. I know that phi is going to be equal to 0 in this case because I know that I need y as a function of 0, 0 to be equal to 0. So the sine of 0 equals 0. So now what I can do is I basically need to use the information given in the problem and then solve for k, solve for omega, and solve for a. So I know that the amplitude is 0.1 meters, so that's already taken care of. And so now I have to try to figure out what k is, right? And so I can say that k is going to be equal to 2 pi over lambda. And so I have to figure out what lambda is. And in order to do that, then I can say that I know the frequency, right? The frequency is 10 hertz, and the speed is 100 meters per second. So I know that if the frequency is 10 hertz and the speed is 100 meters per second, I know that the speed is equal to the wavelength times the frequency. And so that then is going to allow me to say that lambda is equal to v divided by f, which is going to be equal to 100 meters per second divided by 10 cycles per second, which is a hertz, which is going to be equal to 10 meters. So now I have that the k is equal to 2 pi divided by 10 meters. And that's going to be pi divided by 5. Now it's traditional just to write everything in SI units, and then it's implied. If things are not in SI units, then you have to include them. So pi over 5 would then have the units of inverse meters. So I now have my k, and I have to find omega. So omega is going to be equal to k times v, right? Because v was equal to omega over k. So that's going to be equal to pi over 5 for k times v, which was 100 meters per second. And so then that's going to be equal to 20 pi. And the units of this are going to be radians, because it's an angular frequency, per second. So at this point, then I'm ready to just plug them into the final expression. I can get y as a function of x and t is equal to a, which is 0.1 meters, times the sine of kx, so that'd be pi over 5 times x, where x would be in meters, plus 20 pi times t, where t would be in seconds, and then that's the radians per second. And then that would give me my final expression for the equation of this wave, so that I could plug in any value of x and t, where t would be at what time it is, and what is that specific particle doing at that time. And so then that describes fully the entire wave. And then part B, what is the max transverse speed of a particle on this string? Well, we want to just remember that the max transverse speed is equal to omega times a, so that's going to be equal to 20 pi times 0.1, which is equal to 2 pi meters per second. So a difficulty here is that you just have a lot of variables, and you have to know what they are, and you have to know when to use which equation. And then you have to be able to know that they exist so that you know to go find the equations you need in order to solve for what you want. So a lot of it comes down to the vocabulary, kind of getting your visual and your conceptual understanding of what's happening with the wave correct, so you know what y is, you know what x is, and you understand that you can describe the wave as a function of time. Okay, so we'll be talking a lot more about wave motion in class. If you have any questions, please let me know.